What are polymers? The field of polymers is so vast and the applications are so varied that it is important to understand how polymers are made and used. Since there are over 60,000 different plastics, companies manufacture over 30 million tons of plastics each year and spend large sums on research, development, and more efficient recycling methods. The chemical reaction in which high molecular mass molecules are formed from monomers is known as polymerization. There are two basic types of polymerization: chain reaction or addition, and step reaction or condensation polymerization. Chain reaction polymerization. This type of polymerization is a three-step process involving the two chemical entities, monomer and at least one carbon-carbon double bond. Ethylene is one example of a monomer. It is used to make a common polymer. One way to produce polymers is free radical polymerization, which has three stages: initiation, propagation, and termination. As an example, let's look at the polyethylene. To begin, we need to add a catalyst to our supply of ethylene, which when heated has the habit of splitting into two fragments, each with one unpaired electron or free radical. These fragments are known as initiator fragments. The unpaired electron naturally seeks another and finds a convenient target in the double bond between the carbon atom and the ethylene molecule. Taking an electron from the carbon bond, the initiator fragment bonds itself to one of the monomer's carbon atoms. The initiation reaction creates another free radical associated with the ethylene molecular other carbon atom, and so ethylene monomer begin attaching themselves in the chain, creating new radicals each time and lengthening the chain. This stage is called propagation. Eventually, free radical polymerization stops due to what are called termination reactions. Instead of stealing an electron from double-bonded carbons or nearby propagating chain, the carbon atom with a free radical sometimes steals an entire hydrogen atom from another chain end. Ionic polymerization is another type of chain reaction. Ionic polymerization can be anionic and cationic. In the first case, the electron is withdrawn, while in the second case, the electron is donated. In anionic polymerization, the electron density is decreased on a double bond and facilitates the attack of anionic species such as cyano and carbonyl, while in cationic polymerization, density is increasing on the double bond and facilitates the attack of cationic species such as alkoxy, alkyl, alkenyl, and phenyl. Step reaction polymerization is another type of polymerization. This polymerization method typically produces polymers of lower molecular weight than chain reactions and requires higher temperatures to occur. Unlike addition polymerization, stepwise reactions involve two different types of defunctional monomers or end groups that react with one another, forming a chain. Condensation polymerization also produces a small molecular byproduct. Here's an example of formation of nylon 66, a common polymeric clothing material involving one each of two monomers, hexamethylene, diamine, and adipic acid, reacting to form a dimer of nylon 66. Polymer is an organic material, and the backbone of every organic material is a chain of carbon atoms. The carbon atom has 4 electrons in the outer shell. Each of these valence electrons can form a covalent bond to another carbon atom or to a foreign atom. The key to the polymer structure is that 2 carbon atoms can have up to 3 common bonds and still bond with other atoms. The polymer chain is often shown in 2 dimensions, but it should be noted that they have a 3-dimensional structure. Each bond is at 109 degrees to the next, and therefore the carbon backbone extends through space like a twisted chain of Tinker toys.
Linear polymers consist of long strands of polymer chains joined end to end. These polymers have high density, resulting in a greater strength. This efficiently packed structure forms basic polymers such as polyethylene, nylon, and fluorocarbons. Branch polymers are formed when side chains are attached to main polymer chains. This effect causes the strands to not fit as neatly together, resulting in a lower density and a lower strength. Similar to how there is no perfect crystal, linear polymer structures also contain some branched polymers. Low-density polyethylene is an example of a linear polymer with short chain branches. High-density polyethylene consists of mostly linear chains, although branched chains do occur throughout. Cross-linked polymers are formed by linking linear polymer chains together with covalent bonds. This structure can form naturally during synthesis are most often created with irreversible chemical process. Cross-linked polymers take on additional strength and gain heat resistance. Examples of this include elastic rubbers. Ultra-high molecular weight polyethylene is formed with extremely long polymer chains, resulting in a very tough material. It's highly resistant to corrosion, 15 times more resistant to abrasion than carbon steel, and a low coefficient of friction, making it ideal for applications such as knee and hip replacements and spinal implants.
There are two types of polymers, crystalline and amorphous. The arrangement of amorphous polymers are very unorderly, while crystalline has a distinct structure to the molecules. A polymer can be 100% amorphous, but not 100% crystalline. This is a semi-crystalline polymer, which has areas that are either of the two types. To portray the crystallinity of a polymer, we use a formula that takes the density of the sample, the density of a theoretical perfectly crystalline polymer, and the density of a perfectly amorphous version of the polymer. This then tells us how much the polymer is actually crystalline, with the rest being amorphous. Amorphous polymers tend to be glassy and clear when they don't contain fillers, fairly brittle, easy to thermoform, soft, and have low shrinkage. These are two common examples of plastic polymers, polyvinyl chloride and polystyrene. They have similar glass transition temperatures, which is the temperature at which they go soft. So when using these polymers, you don't want the conditions to go above those temperatures as they may fail. The structures are both similar, being a basic 2-carbon structure with different functional groups, and repeating for n number of times. Crystalline, on the other hand, can be translucent or opaque. They are strong, hard, rigid, and have a sharp melting point. They have much lower glass transition temperatures than the amorphous polymers, except for PETE. For crystalline polymers, there is not much physical difference with the polymer above and below the glass transition temperature, since even though the amorphous sections can move, the crystalline part still gives the polymer structure. The melting point, however, is when the crystalline bonds begin to break, allowing the polymers to melt. As with amorphous with glass transition temperatures, use of the polymer should stay below these melt temperatures to avoid failure. Common examples of crystalline plastics are low-density polyethylene, high-density polyethylene, polypropylene, and polyethylene terephthalate. The difference in the two polyethylene polymers are the way the molecules interact, either linear or branched. The structure of these are fairly similar to the amorphous plastics, with the same 2-carbon chain with differing functional groups. The outlier is the polyethylene terephthalate, which has a much different structure, which leads to its much higher glass transition temperature and melting point temperature. Here's an example of a differential scanning calorimetry graph, or DSC graph, which is used to identify unknown polymers. The polymer is melted or quenched over a temperature range, and the temperatures associated with the polymer show up as heat flow. The first minor drop is associated with the glass transition temperature of the polymer, which can oftentimes be hard to see. For this polymer, it's at about 75 degrees Celsius. The next important feature is the big release of heat, which signifies the crystalline bonds breaking. This would be the melting point temperature, which is at about 250 degrees Celsius. From these temperatures, and looking at a list of common polymers, we can see that this is PETE. We can then find the crystalline temperature of PETE by quench cooling the polymer. This is the reformation of the bonds that were broken at the melting point temperature, which is at about 140 degrees Celsius. DSC is a very useful tool for reverse engineering, since you can determine the composition of a polymer, or the important temperatures for your polymer.
Defects in polymers differ from metallic and ceramic material. Due to the structural properties of polymers, defects are only considered to occur in crystalline structures. As the nature of amorphous material, defects are so abundant that the information they provide is almost useless. For all intents and purposes, the amorphous region is one big defect. Polymers have more complex defects as the connectivity between structures behaves completely different. A macromolecule defect can affect several microstructural features at more than one length scale, and a point defect can play a part in controlling macroscopic properties. The way chains interact with each other in polymers cause them to react differently than previously seen. These effects can occur in crystalline regions in polymers. Similar to traditional defects, vacancies occur when a chain ends, because the chemical properties are different to those of a normal chain. Interstitials can occur with impurity atoms or ions, either through a main chain or side branches. Non-traditional defects include discontinuation of chains, loose chains, chain boundaries, branches, crystalline boundaries, and surfaces of chain folded layers, as they are boundaries between adjacent crystalline regions.